All right, good morning, folks. Let's get started as a group here. What can you say about a polynomial such as this? What can you say about it? You're just standing around talking with friends. Hey, take a look at that polynomial. What do you think about it? Any observations?
Even degree.
It appears to be an even degree because the first term that you see is 3x to the 4th, which means it would look like, yeah, it looks some sort of parabola-ish shape. What else can you say about it? Jackie? You have 4 classical x-intercepts? Anything else? What else might you say?
10.
So you get the constant term there, 10. What does that represent? The y-intercepts. We have a y-intercept there. Anything else that you might say about this? Because it's a bit of a trick question. A few of the things we've said so far are not correct. Everybody see what makes it a trick question? Paris? Yeah, those 3x to the 4th terms cancel out. And so then what do we actually have left out? Left over? We actually just have negative 5x cubed plus 10. So now how does that change our analysis? Now the leading term is a cubic. So it would be like that, except the first term is negative, so instead it would look like that. So now what we have is a cubic that looks like this. We still have a y-intercept of 10. That didn't change. So if I wanted to start making my graph, I'd have a y-intercept of 10. And then I would know that I would have at most 3 x-intercepts. And then my tail to the right would go down and my tail to the left. Okay. I think that's all there is to say about that one. So we want to be careful. Make sure that all of our terms are written in order. So in this particular case, they started writing in order, but then that term canceled out that one. So you've got your leading term, which tells you about end behavior, as well as how many potential x-intercepts you have. The last constant term tells you where your y-intercept is. And then you have to start the process of actually finding your x-intercepts, which is the main bulk of the work that we do in here. Okay, what can you say about this polynomial?
4th degree.
Yeah, it appears to be 4th degree. No trick question here. Once you multiply, you'll have x to the 4th. So it's a 4th degree. So this one really will look like that parabola with the tails pointing up. What else could we say? Is the y-intercept 24? Let's see. Negative 3 times negative 1 is 3. Times 2 is 6. Times 2 times 4 is 24. So yeah, the y-intercept would be 24. Again, when you have it factored like this is really nice because you can see the x-intercepts. We could all list off the x-intercepts as positive 3, positive 1, negative 2, negative 4. And then you can do the lazy person FOIL and just multiply the first terms to get x to the 4th. That'll tell you your end behavior. And then you multiply all the last terms to give you the y-intercept, which would be 24. By the way, did we talk about last time how it's not really fair that I call it the lazy person's FOIL? Yeah, the efficient person's FOIL. That's right, because you're just doing what matters. Okay, likewise for this one, we can keep going now. When you do synthetic division, what does the last number represent? There's at least 2 different ways that we can describe it. What's the last number? So I do synthetic division. Maybe I'll do it on, well, I'm just going to make one out of 1, 3, 4, 2. And then I'm going to do synthetic division with a 7. And so then I drop the 1, and then I get 7, 10, 70 minus 4 is 66. Oh, I don't even know what that multiplies to be. 462, and then 464. What does that last number represent? Yes, the remainder. It's perfectly called. That is the remainder. And so that either means input, output, that we now know we have the coordinate 7, 464. Is that an x-intercept? Definitely not. That's like way up there. So it's not an x-intercept. And if I were to now take whatever polynomial this was, I could then break this down into these 3 parts and say I partially factored it into x minus 7, and I'm presuming that started as a cubic, so now this is squared. So then I'd have x squared plus 10x plus 66, and then plus the 464, which would be the remainder. Okay, so those are the various parts and pieces of synthetic division and polynomials that we were talking about last time. And we already covered the last question. What do the first and last number represent? Their coordinate. So let's keep going. Today, is a very quiet day. Morning, everyone. February 25th, this is our last week in February. Today we're going to wrap up, or try to wrap up anyway, chapter 3. We may not get all the way through it, but we'll try. And then we have next week to cover some parts of chapter 4. And then we have spring break and then a test when you come back. Now let's see, my note is very old. Everyone already received their tests. Did I already tell you both of these jokes about hardcore kids? Oh, I did. Well then, I need to tell you a new joke. Let me see here. Otherwise, we're going to proceed. I think we got to here, right? We started section 3.3? Or did we just look at it? No, we did, because it was rational zeros there. We started talking about it, and which ones did we actually do? Number 1, number 2, which ones did we do?
Page 12.
So we did number 4? We didn't do 1, 2, 3?
We did 1, 2, and 4.
Oh, we did 1, 2, and 4. Okay, perfect. Okay, and that was just looking at the rational zeros theorems. Now let's see here. So let's do one of those together as a review. Let's look at number 5. Let's remind ourselves how to do the rational zeros theorem. And then we're going to go back and talk about Descartes' rule of signs. So everybody looking at number 5? Now I'm going to share something with you here about number 5, which is going to sound strange, but no stranger than some of the other things I've said. And that is that going forward, what you're really going to be tested on the test for this section is I'll just hand you a polynomial, like this one, and I'll say, find the x-intercepts, right? Because we already know the end behavior, it's a cubic, so it looks like that. And then we already know the y-intercept is 6, so we know where that is. But I would say, find the x-intercepts. And that would just be a very open-ended statement, and I'd say, go. And then your job is to go find the x-intercepts. Well, the formal way that I'd like you to find the x-intercepts is to use the rational roots theorem. And so looking at number 5, the rational roots theorem, or rational zeros theorem, states that you create a fraction, and in the numerator, you put all the factors of the last term, that is the y-intercept. You take all the factors of 6, so that would be 1, 2, 3, and 6. And you divide them by all the factors of the leading term, which is a 1. And so the only factors of 1 are just 1. And then you make every possible fraction out of those. So I would actually draw little lines for myself. 1 over 1, 2 over 1, 3 over 1, 6 over 1. And that gives me the numbers 1, 2, 3, or 6, and plus or minus. So that is the list of the potential x-intercepts. And that's it. Those are the only potential x-intercepts. That is, that are whole numbers or fractions. There could be x-intercepts that are square roots. Remember, we did a problem the other day where the polynomial factored into x plus root 3 and x minus root 3. So there could be an x-intercept that's a square root. But what we're saying is that this rational roots theorem tells you a complete list of any potential whole number or fractional x-intercepts. So that's it. All you have to do now is walk your way through the list of checking 1, check -1, check 2, check -2, check 3, check -3, check 6, and check -6. You just walk your way through that list, trying each and every single one of them until you find your x-intercept. Erica? Say what?
It's supposed to be a 5.
What's supposed to be a 5?
The 3.
The 3. That? What about it? Oh, this isn't the coefficients. This is me taking the last number, which is the 6, and writing down all the factors of 6. And then the first number, which is a 1, and writing down all the factors of 1, which is just a 1. And then making every possible fraction. I can see why that looks like that should be the, I'm not talking doing the coefficients yet. I'm about to do the coefficients. I'm about to write down 1, -2, -5, and 6. And we're about to do synthetic division using each and every single one of those numbers until we find an x-intercept. Okay, so now this is the part that might feel a little, I hate to even say it, monotonous or trial and error, like where you just sit there and you start trying numbers. But that's the nature of it. So I will go ahead and just try the first one. I'll try 1. So I've got the 1, that's 1, multiply, add, multiply, add, multiply, add. And look at that, we already found it. Right, so I mean, just because it's a guesswork type of procedure doesn't mean that it's terrible or that it will take a very long time. You could look out, and it could be one of the first numbers on the list. So what have we now found out? We have, we started as a cubic, so now this reduces down to an x squared x no x. My 1, that, and my remainder, this now becomes the polynomial x minus 1, x squared minus 1x minus 6, and plus a remainder of 0. All right, so remember, this is our basic procedure of how to read synthetic division. We started with the cubic, x cubed minus 2x squared minus 5x plus 6, and now I have x minus 1 times x squared minus 1x minus 6 plus 0. Now this plus 0 at the end, do I even have to write it down? I mean, I don't really have to write it down because it's 0, so that would go away. And so what that means is we have successfully factored one factor off of that polynomial. And now once you get down to a quadratic, you can just factor it using your normal factoring skills, or if it wasn't factorable, you could use the quadratic formula. This one, is it factorable? What can you multiply to make 6 to add to make 1? Yeah, 3 and 2. So we can go ahead and factor this one now. It's x minus 1. And then x minus 3x plus 2. Is that what everyone else got? Did we already do this one together? Okay. All right, well, we did it. So for this polynomial at number 5, we started, and by the way, we're going to make a graph now. We started out just knowing that the y-intercept was 6 and the end behavior was a cubic. So I'm going to draw myself a little reminder here that my end behavior will look like this, and my y-intercept is a 6. And now I can also jot down what all my x-intercepts are. So my x-intercepts are positive 1, positive 3, and negative 2. So I'll jot those down on my graph. So 1, 2, 3, 1, 3, and negative 2. Now this one, we just have a whole bunch of dots, right? How do we turn this into a graph? Where do I attach my end behavior tails? How do I do those? Where do I put this tail on the right? What do I attach it to? Yeah, I attach the tail on the right to the furthest rightmost x-intercept. And then where do I attach my tail on the left? To the furthest left x-intercept. And then at this point, it's just a matter of connecting all the dots. You'll notice that in this particular factorization, every single one of those x-intercepts, every single one of those factors was to a power of 1. So the multiplicity is a 1, which means it just slice, slice, slice. So there's no bouncing off the x-axis, you're just slicing through. So starting here on this tail, I come up, and down, up again, and that's what my graph looks like. So that was a simple example of doing an entire problem, where you'll notice we never looked at our graphing calculator once, right? And yet we still ended up finding all 3 x-intercepts, and it boiled down to the fact that the rational roots theorem gave us a list of x-intercept candidates. These were our candidates. And the very first one we tried worked out, and we were able to factor the rest. What questions would you like to ask about this process? Well, then let me tell you now, whenever you have a problem like this, so let's just say we already did, are you telling me that we already did 3, 4, 5, and 6? Or, we did, no, 5 we just did. We didn't do 6 yet. But we've done 1, 2, and 4 so far. Josh?
I do have a question.
Yeah, go ahead.
So I believe over here, that's the first one. When you get the new polynomial,
Yeah, the new one right here.
yeah, do you have to find, well, it's going to be the same factors, the numbers, but would it always be like that for the last?
Oh, right. Good point, Josh. So when you get to the next reduced polynomial, well, now, first of all, I mean, this is a quadratic, so you don't have to do synthetic division again. You wouldn't even have to list out the rational roots theorem, because at this point, it's just a quadratic, and in theory, you can just factor a quadratic. But if you started with like an x to the 5th, and then you got down and now you're x to the 4th, yes, you would want to do the rational roots theorem all over again. Because if this number, let's say you started out with the number like 20, and so you had all the numbers that go into 20, but then you just reduced to a polynomial that only had the number 10, then you would want to do the rational roots theorem again, because now your list will be smaller. You wouldn't want to check more candidates than you have to. Yeah, that's a good question. Okay, so With this general open-ended challenge of saying, here's a polynomial, go find the x-intercepts, and you're going to write out the rational roots there and look at this long list of candidates, and you're going to say, I have to sit there and search this. I will go ahead and tell you that so long as you tell me the rational roots theorem and show me what they are, you can feel free to go ahead and just use your calculator, graph it, and see what the x-intercepts are. And that way, you're not wasting a whole bunch of time trying tons and tons of numbers, when in fact, you can just look it up on your calculator, right? You all have a calculator. So for this particular problem, I could just type in x cubed minus 2x squared minus 5x plus 6. And I can just look at my graph and say, well, there they are, -2, 1, and 3. Now, so here's what I'm saying and what I'm not saying. You can't just look up the graph and calculator and say, aha, I'm just going to write down the factorization. Because now that I can look at my roots, I can just say it's x plus 2, x minus 1, x minus 3. That's too much. You're not allowed to just look at the graph and then just write them down. You still have to show me the work of the synthetic division and the factorization. So, but once you look at the graph and you can say, okay, well, my easiest number for synthetic division is a 1. So I'll go ahead and do the 1, do the synthetic division, show how that factors it, and then factor the rest. All right? So you still have to show me all the work. You're not allowed to just look at the graph and then just write down the factored form. That would be skipping too many steps. But you are allowed to use your graph to narrow down this list to say, okay, well, yeah, there's rational roots theorem, that's what it states, but now I know that my x-intercepts are those numbers right there. And so now you can just try those. Is that fair? Okay. I'm allowing you to kind of cheat and know which of the numbers on your rational roots theorem list are the real x-intercepts, but then you still have to do the work. Okay. Josh, thanks for your question. Anybody else want to ask a question before we keep going? All right. So that was number 6. We have a few more problems to go. Let's go back now and look at Descartes' rule of signs. This one is quite interesting. We are going to use it as helpful. So you all recall who Descartes is, right? Descartes is the namesake of the Cartesian coordinate grid. He also, did we ever watch that video? I think we did, where of cognito ergo sum and the demon argument. All right, so Descartes' rule of signs, so one more thing that he's known for, is, let's just say that you have a polynomial. So, in fact, we're going to go back and start over with number 1 because we're going to practice this a few times. So let me start with number 1. That's, isn't that the one we just did? X cubed minus 2x squared.
Yeah, they're repeated on the other page.
Oh, it's repeated. Okay, well, thank you, Chantal. All right, so let's look at how Descartes' rule of signs works. It says, well, I'm going to tell it to you before we actually read it. We're looking at this polynomial, and we'd like to know how many, where are the x-intercepts? That's our goal. What are the x-intercepts? Well, Descartes' rule of signs gives you a really interesting result that tells you the number of x-intercepts that are positive over on the right-hand side, and it'll tell you the number of x-intercepts that are negative on the left-hand side. Isn't that interesting? It's a very general result that will tell you, hey, for this given polynomial, there's actually going to be 2 positive x-intercepts and 1 negative x-intercept. It's a very abstract result that Descartes came up with this method that he said, well, I don't know where they are yet, but I know that I should have 2 over here on the right, and I should have 1 over here on the left. That's really interesting. That's what this result is going to tell us. So let's see how it works. Suppose f of x is the formula for a polynomial, written in the descending powers of x, so that's what we have. P denotes the number of variations of sign in the formula for f of x. Then the number of positive real zeros, again, x-intercepts, is one of the numbers p, or p minus 2, p minus 4, and you count down until you get to 0. So let's read this again. P denotes the number of variations of sign in the formula. So what we're going to do, everybody put a little plus on the first x cubed. You're just going to count the number of times the sign changes. So you'll notice that it goes plus to minus to minus to plus. So how many times does it change? If I start at plus, and I go from plus to minus, did it change? Yes, that's one change. Then it goes from minus to minus, did it change? No, that's not a change. Then it goes from minus to plus, did it change? That's a change. So P is 2. P is 2. That's the number of times the sign changed. And then what you do is you take that number 2 and you start counting down by 2s until you get to 0. So this one's pretty easy. 2 minus 2 is 0. And if I kept going, 0 minus 2 would be negative 2. But these are the number of x-intercepts on the right-hand side. You can't have a negative number of x-intercepts. So what this tells me is the number of x-intercepts I have over here on the right is either 2 or 0. That's a pretty fascinating result. I now know that for this polynomial, how many positive x-intercepts will I have over here? Either 2 or none. That's what it says. So that way when I start looking through my list of x-intercepts, I know ahead of time that I should either expect to find 2 positive x-intercepts or no positive x-intercepts. That's actually really helpful because if I already found 1, then what do I know? Yeah, there's going to be 1 more. I should keep looking because there's at least 1 more positive x-intercept. All right? So that's P. P is the number of positive x-intercepts. And again, that just means the number of x-intercepts over on the right-hand side. Okay, well, that's the first part of the test. The second part of the test is N denotes the number of variations of sign in the formula f of negative x. Now what that means is you take your function and you plug negative x into it. What that really means is that you just change all the signs on the odd-powered terms. So everybody, this was our original function, right? Now I'm going to write down f of negative x. And what that means is just go up to the cubic and the power of x to the 1, and just the terms that are odd powers, so x to the 3 and x to the 1, change those signs. And we don't even have to write out the whole polynomial again. Let's just write down the coefficients. So these coefficients were plus, minus, minus, plus. And if you had wanted to, you could have just written that, plus, minus, minus, plus. And then you could have counted 1 change, no change, 2 changes. So that gives the 0. What we're going to do now is take these signs and only change the sign on the odd-powered terms. So this is actually going to be a minus, still a minus. This will become a positive, still a positive. That might have felt a little arbitrary. My instruction was change the sign on the odd-powered terms. So that plus is becoming minus, and that minus is becoming plus. Now we just do the same thing again. We count how many times the sign changes. And that's going to be our n. N is the number of negative x-intercepts that we have. So how many times did the sign change? Negative to negative didn't change. Negative to plus did change. Plus to plus didn't change. So that's a value of 1. There was 1 sign change. And now, as before, you start with that number and you start subtracting by 2. Well, 1 minus 2 is negative 1. And so I'm already done because I can't have a negative number of x-intercepts. And so what this tells me is that I will have exactly 1 negative x-intercept. So no matter what, I know I am going to end up with 1 negative x-intercept. So I need to keep looking for it until I find it. And on the other hand, I might have either 2 positive x-intercepts or none. So consider this abstract result in and of itself tells me that my graph is either going to look like that or like this. So it'll either be up, down, up, or it would be up, down, up, in which case my little dip over here doesn't touch the x-axis. This is what Descartes' rule of signs is telling me. It's giving me a very abstract result stating that in this polynomial, I already know ahead of time, I'm either going to have 2 positive x-intercepts or none, and I'm going to for sure have 1 negative x-intercept. And so now I know that my graph will either look like this or this. Yep. So that was just walking us through the first example. We're going to do this at least 4 or 5 times so that we can all get the hang of it. So what was that, number 1? Can we do number 2? Does everyone have space right there where you can read out those signs? We're just going to practice the Descartes rule of signs. We're not going to be factoring all the way through. We're just going to practice the Descartes rule of signs. So try this out with me here. Let's look at number 2. There we go. So number 2. First of all, are all of the terms listed? It goes x to the 4th and then it skipped x cubed, didn't it? So we have to fill that in. So everybody, let's start by just writing down the function. Just write down the function. This will be a very concrete way of doing Descartes' rule of signs. Write down the function. So 1x to the 4th plus 0x cubed minus 9x squared minus 4x plus 12. So first of all, that's our polynomial. That would be the polynomial that you would do synthetic division on. Now, to be fair, is 0 positive or negative? Zero is neither positive nor negative. So in terms of the Descartes rule of signs test, this term is a little irrelevant because that 0 is not positive or negative. So then what are our signs? Let's start by just writing down the signs. So f of x, the signs that we have are positive, negative, negative, and positive. So those are the signs for the original polynomial. And now let's count for p equals the number of sign changes. So from positive to negative, that's one change. From negative to negative, that's no change. From negative to positive, that's 2 changes. So our p is 2 because there were 2 total sign changes. And then again, at this point, you would start subtracting 2 and making a downward sequence of numbers until you reach 0 or negative. In this particular case, 2 minus 2 is already 0, and that's the end of our list. Okay. So the total number of positive x-intercepts is either there are 2 of them or there are none of them. Okay, now let's write down f of negative x. So what we want to do is just change the sign on the odd-powered terms. So x to the 4th is even, that doesn't change. X squared is even, that doesn't change. X to the 1, that's an odd number, so that one will change. And this is x to the 0, which is technically even, so that one doesn't change. So what do we have then? We still have a plus. This one is still minus. This one is going to change from minus to plus. And this one is still plus. So all we did was change the signs on the odd-powered terms. So now that's going to tell us the number of negative x-intercepts. So again, counting the sign changes, plus to minus, that's one change. Minus to plus, that's another change. Plus to plus, that's no change. So the total number of sign changes was 2. And once again, starting at 2, you start subtracting 2 until you get to 0 or a negative number. 2 minus 2 is 0. And that's the end of our list. We're going to do a full analysis here. What this tells us is, first of all, we don't know what the x-intercepts are yet. But I know that we either have 2 to the right or none to the right. And I either have 2 to the left or none to the left. So what are all the different possibilities? This is interesting to think about. What are all the possibilities? What if I have 2 to the right and 2 to the left? Is that one possibility? Yeah. What if I have 2 to the right and none to the left? That's a possibility. What if I have 2 to the left and none to the right? That's a possibility. Or what if I have none to the right and none to the left? So what would those 4 drawings look like? What would those graphs look like? This graph would look something like that. That would be 2 x-intercepts to the right and 2 to the left. This graph would look like that. Only 2 x-intercepts to the right. Nothing over on the left-hand side. This graph would look like this, 2 to the left and none to the right. And then this graph, the whole thing, would be floating up above the x-axis. This is the power of Descartes' rule of signs. It tells us ahead of time the basic structure of what the polynomial is doing. And now all we have to do is actually go find those x-intercepts. And it's just telling us ahead of time how many there could be. What do you folks think about this? Are you thinking, who is this Descartes guy? What is this all about? Well, that's how Descartes' rule of signs works. It's telling you ahead of time where to look for x-intercepts. So again, the power here would be that if you now did the rational roots theorem, so I'm going to do the rational roots theorem on this one just to show it to you. I'm going to create the fraction. So all the factors of the last number is 12, so all the factors are 1, 2, 3, 4, 6, and 12, over all the factors of the first number, which is just 1. And so I make all those possible fractions, and that tells me that my x-intercepts are plus or minus 1, 2, 3, 4, 6, and 12. So those are all the possible numbers I need to look through until I find my x-intercepts. And basically what it tells me is that the minute I find an x-intercept, like let's say that I find the x-intercept is the number 2, well, I now know I need to go look for one more positive x-intercept. Because if I have one positive x-intercept, I must have 2 of them. So now I need to keep looking. And if, while doing synthetic division, I find that one of my x-intercepts is -3, well, now that tells me I need to keep looking until I find another negative x-intercept, because it's bound to be there. Okay, well, that's all the theory behind it. Let's just practice Descartes' rule of signs a few times now. Everybody, let's look at number 3. And again, I just want to show you a concise way of writing this down. Here's number 3. And I would start by writing out the function. So -17x cubed plus 5x squared plus 34x minus 10. And what I'm going to do is I'll first write down f of x, and I'll just write down the signs after verifying x to the 3, x to the 2, x to the 1, x to the 0. So my signs are minus, plus, plus, minus. And we're going to count p, the number of times the sign changed. So again, minus to plus, that's 1 change, plus to plus, that's no change, plus to minus, that's another change. So my p is 2, or start subtracting by 2. It's either 2 or no positive x-intercepts. And then I want to do f of negative x, which means change the sign on the odd terms only. So if I change the sign on the odd terms only, this one becomes plus, that term is still positive, this term becomes minus, and that term is still negative. So now I count the number of sign changes. So plus to plus is no change, plus to minus is 1 change, minus to minus is no change. So that means n is equal to 1. And if I start subtracting by 2's, 1 minus 2 would be -1. I can't have a negative number of x-intercepts, so I'm done. What this tells me is that for this cubic, I definitely have one negative x-intercept. So now I know for sure when I do synthetic division, I need to try a negative number, because there will be a negative x-intercept. And I either have 2 positive x-intercepts or none. Keep in mind, though, even this result, saying that I have 2 positive x-intercepts or no positive x-intercepts, what that really means is, oh no, yeah, no, that's it. You're looking for 2 or none. The 2 x-intercepts could be square roots. Like you might still have to consider the fact that your 2 positive x-intercepts could be square roots. So, they might not have shown up on your list from the rational roots theorem, but you either have 2 or none. Okay, so look, that was number 3. Let's try number 4. So again, you would jot down your polynomial. So f of x equals 2x to the 4th plus x cubed minus 7x squared minus 3x plus 3. So the first thing we'll do is write down the signs for the function as it is. And so what is it? Plus, plus, minus, minus, plus. Those are the signs for the original. And so how many sign changes do we have? None, 1, none, 2. So p is either 2 or 0. So you either have 2 positive x-intercepts or no positive x-intercepts. And now let's consider the function where you change all the odd terms. So the x to the 4th stays positive, x cubed becomes minus, x squared stays negative, x becomes a plus, and that last term stays positive. So now how many sign changes do we have? Plus to minus is 1, minus to minus is not a change. Minus to plus is another change, plus to plus is not a change. So now the number of negative x-intercepts is either 2 or 0. Okay, I'll ask again. How do you all feel about this? I know it's a quiet Monday morning. Only a few of you have spoken thus far. But what do you think about this? Is this potentially one of the weirdest things you've ever seen in a math class? I mean, it's not algebra, right? We're not multiplying numbers, we're not adding numbers, we're not doing any real math at all. We're counting how many signs pluses become minuses and minuses become plus. It's pretty weird. It's a very weird result. Anyone? No? All right. Well, then let's keep going. So what, then we've done 4 of these so far. Let's go ahead now and move on and try a full problem. So how about number 7? We haven't done 7 at all, right? We haven't done anything on number 7? Okay. So let's do a full analysis of number 7. We have this polynomial. Oh, yes, Karis, go ahead. Wait, say what?
7 is the same as exercise.
Oh, it is, but we didn't do number 3, right?
All the problems on page 12 are the exact same thing.
Really? How did that happen? Did I just accidentally photocopy the same page twice?
Maybe you wanted one side for.
You're right. I think that is what I wanted. Yeah, you're totally right. Okay, well, wait. Oh, right. Yeah. That must have been what I did. So they are all the same. Okay, well then let's skip all the way and start. Let's go all the way then to number 9. Good idea. Okay, so we're going to try a full problem here, and we're going to do this in the way in which we would approach this problem. Okay, so number 9. We're looking at this polynomial, and we're saying to ourselves, all right, I've got this polynomial, f of x equals 3x to the 4th minus 14x squared minus 5. And first of all, what's our goal?
The x-intercepts.
Do we want the x-intercepts? And the y-intercept? And the behavior, so that we can graph it. Right? Our end goal is to graph it. We want to be able to graph this thing. We want to be able to say, okay, there's a polynomial. Here's a nice graph that I just did by hand off the top of my head without looking at a calculator. Okay, that's our end goal. We're doing pretty much everything in this class. Our end goal is to be able to look at a function and then make a hand-drawn sketch. Okay? So we're looking at that and we're saying, well, I already know a lot. Right? We already know that the y-intercept is -5, so I can go ahead and put that on my graph. All right, start a graph with me. I already know my end behavior is x to the 4th, so my end behavior looks like this. So I got that going for me. So far so good. We know those two things, but now we need to find all the x-intercepts. So this is how you might go about this. Say, okay, I want to find the x-intercepts. First thing we'll do is the rational zeros theorem or the rational roots theorem. So rational roots theorem, we're going to take every factor of the last number. So maybe I'll write this out in words first. We take every factor of the last number, divide by every factor of the first number. So that gives us, the last number is 5, so the factors of 5 are 1 and 5. And the first number is a 3, so the factors of 3 are 1 and 3. And we're going to create every possible fraction. So that's 1 over 1, 1 over 3. Or that's 5 over 1, 5 over 3. And that gives us the list. So 1 over 1, or 1 over 3, or 5 over 1, or 5 over 3. And just to make that a little more clean, because we don't want to look at numbers like 1 over 1 and 5 over 1, you would say plus or minus the numbers 1, 5, 1/3, or 5/3. Those are all the x-intercepts that could exist as whole numbers or fractions. Keeping in mind there could be square root x-intercepts that we don't know about. But this test at least tells us which x-intercepts could be whole numbers or fractions. So that's one thing so far. That's where all of our possible x-intercepts are as fractions or whole numbers. So then we'd say to ourselves, well, where could they possibly be? Let's do the Descartes' rule of signs. Descartes' rule of signs. Because that'll tell me how many x-intercepts over on the right-hand side and how many x-intercepts I have over on the left-hand side. So I'm just going to write down f of x, but It's positive, negative, negative. So those are my signs. I had the positive 3, negative x squared, and then a negative 5. And how many sign changes is that? Well, plus or minus, that's one sign change. Minus, minus, that's not a sign change. So p equals 1. And if I count down from that by subtracting 2, 1 minus 2 would be negative 1. I can't have a negative number of x-intercepts. So that's it. That tells me for sure I have one positive x-intercept. So I can expect to find one x-intercept over here on the right. I'm not actually going to draw that in because I don't know where it is yet. But I do know now that I should be able to find one positive x-intercept. Okay, so then the rest of the Descartes' rule of sign says to do f of negative x, which means change the sign on the odd numbered terms. Where are the odd numbered terms? Where are the odd numbered? That is an odd exponent. Do I have any odd exponents? No, so I don't change any signs. I still have plus, minus, minus, which means the number of x-intercepts is either 1 or that's it. Now I know for sure that I have one of each. I have one positive x-intercept and one negative x-intercept, and that's guaranteed. So as I start looking through this list of numbers, I will find one positive x-intercept, and I will find one negative x-intercept. Now again, those x-intercepts could be square roots, so it might not even be on this list, but this is our starting list for looking for whole numbers and fractions. Okay, so far that's our analysis, folks. How do we feel about all that? Going back to my drawing now, I could go ahead and put a dot over here to the left and a dot over here to the right. I don't know where that is yet. And remember, I know my end behavior, so I know that I'll have my tails going up like this. And I'd kind of like you to just appreciate how much we know so far. And we haven't done synthetic division at all. Like just from a very abstract level now, I know my end behavior, I know my y-intercept, I know those are my only potential x-intercepts that are whole numbers or fractions, and I know I have to have one positive x-intercept and I have to have one negative x-intercept. So that's a lot of knowledge that we have so far. All right. Now at this point, we would actually start doing synthetic division. So looking at my polynomial there, we do need to write our polynomial out with all of our missing terms. So what do we actually have? 3x to the 4th plus 0x cubed minus 14x squared plus 0x minus 5. So that means when I go to do my synthetic division, I have to use 3, 0, negative 14, 0, negative 5. You'll notice we didn't need the zeros for the Descartes' rule of signs because 0 is not positive or negative. But we do need the zeros when we do synthetic division. Now, who feels lucky? Which of those numbers should we try? Positive 1, negative 1, positive 5, negative 5, positive third, negative third, or positive 5 thirds, negative 5 thirds? Who wants to try one of the fractions? Nobody. Why would we try the fractions? What, Isaac, what were you going to say? Yeah, might as well just start with 1, right? Let's just try it out. I'm just going to start with a 1. So drop my 3, so that's 3. Multiply, add, multiply, add, multiply, add, multiply, add. That didn't work out. Did I do that right? I went off too fast. Multiply, add, multiply, add, multiply, add, multiply, add. Yeah, so no, 1 didn't work, right? So, in fact, in terms of having a list, I'm actually going to write my list out now. Positive 1, negative 1, positive 5, negative 5, positive third, positive third, negative third, positive 5 thirds, negative 5 thirds. So far we have crossed off the positive 1. Moving on. What number should we try next? Negative 1 as well. So please try again. Drop the 3, multiply, add, multiply, add, multiply, add, multiply, add. Okay, that didn't work out either. Right? So we now know that it's not 1 or negative 1. Now at this point, you can see what we have to keep doing, right? We just have to keep on trying all the numbers until we eventually get there. But this is where I'm telling you that you can go ahead and just use your graphing calculator and see where the x-intercept is, right? Even I can be reasonable. So we're going to go ahead and just graph it. You would take out your TI-82 or your, well, that's really your only option during a test, is take out your TI and you would graph it. And even just graphing it, you'll be able to see just roughly, oh, Now see, this is an interesting example. First of all, was it correct? Is our knowledge correct so far? Did we have one to the left and one to the right? And was our y-intercept -5? And is the end behavior a parabola? Yes. Now, what did we find out here though? Where are my x-intercepts? 2.236 and 2.236, those are actually irrational numbers. So what that tells us is that none of these are going to work. This was just a list of x-intercepts that were whole numbers or fractions. But it turns out that it ends up being plus or minus a square root. So none of those were going to work. Well, that's kind of surprising. I wonder how they expect us to solve something like this. I suppose they want us to factor it. Boy, that was not expected. Well, I think I'm just going to show you an advanced factoring technique on the fly here, because that is apparently what they wanted us to do. Why would they have included an example like that? All right. Oh, that's so sad. You know, part of me wants to just say, let's end our analysis and say that none of these worked, and therefore the only therefore the only x-intercepts would have been square roots. But the other part of me wants you to see how you would have found, what we would have done next. So here's what we would do next. Everyone take a look at, so let's just go ahead and say now that we looked at our graphing calculator, the x-intercepts that you see are not on this list. Therefore, there are no whole number x-intercepts. There are no fraction x-intercepts. And the only x-intercepts are going to be square roots. So everybody, here's an advanced factoring technique for you. It's not that advanced. It's pretty interesting. Go ahead and write down 3x. Write down 3x to the fourth minus 14x squared minus 5. And what I'd like us all to consider here is something called substitution. I want you to notice that instead of 3x to the fourth, that could be written as 3x squared minus 14x squared minus 5. Look what I did right there. I just rewrote x to the fourth as really x squared squared. Is that correct? Yeah. So now what I want us to do is let x squared be replaced by the letter y. This is called a substitution. It allows you to factor higher exponent polynomials. So now I'm going to rewrite that as 3y squared minus 14y minus 5. What you'll notice is that now we just have a normal factorable quadratic. And at this point, we could factor this, just like normal. So we'd say, first of all, there's a number on the y squared term. So we can't just say what multiplies to make 5 to add to make 14. Instead, you multiply the first term times the last term. This is good. We haven't done this in a few days. So 3 times -5 is -15. And then we'll do a factor table for 15. What multiplies to make 15 to adds to make 14? So do 1 and 15 or 3 and 5. So what multiplies to make -15? And since it's negative, it's either positive times negative or negative times positive. So what pair of numbers will multiply to make -15 to add to make -14? Is it positive 1 and -15? All right. So now we can rewrite the middle term, and that gives us 3y squared minus 15y plus 1y minus 5. I chose to write down the -15y first, so that that term would be positive. And how do we proceed from here? What is it called that we do now? We have two different pairs, so we will factor by grouping. So we group the first two, group the second two. From here, we can pull out a 3 and a y. So that's 3y outside of y minus 5. And here we can't take anything out, so we'll just write 1 times y minus 5. And are our two parentheses the same? Yes, they are. So now I know that y minus 5 is one of my factors, and 3y plus 1 is my other factor. Okay, well now that we've done the factoring, we just go back to letting y equal x squared again. So we just did that substitution just temporarily just to allow us to more easily see that we can factor this thing. And then we go back and we call that x squared minus 5 and 3x squared plus 1. And that is our polynomial. It started off as 3x to the 4th minus 14x squared minus 5, and now we have x squared minus 5 times 3x squared plus 1. The important thing here is that now our polynomial is written as a multiplication problem, so that now we can do the zero product rule. We are almost done with this problem, and I swear to you, I'm not going to give you a problem that it would be this challenging on the test, but we might as well finish the problem because we've already gone so far with it. Now at this point, how do we actually now solve for our x-intercept? We have 2 of these left, and by the zero product rule, either this is equal to 0 or that is equal to 0. So you would take either, well, you would take both of them. You'd say, well, on the one hand, x squared minus 5 could be equal to 0, or 3x squared plus 1 could be equal to 0. So let's do one at a time. We're looking for, remember, we're looking for x-intercepts. And so the zero product rule is a way of finding x-intercepts. Normally, what's inside this parenthesis is just something easy like x minus 5, but it's x squared minus 5. So we said each of them equal to 0. In this case, we now move the 5 over. We have x squared equals 5, and then x is being squared, so you square root both sides, and you get x equals plus or minus root 5. Over here on this side, when you move the 1 over, you have 3x squared equals negative 1, and you divide off the 3, and you have x squared equals negative a third. And what happens when you square root both sides? You're square rooting a negative, which is imaginary. So that does not correspond to an x-intercept at all. So my x-intercepts now are at plus or minus root 5. And wouldn't you know, what is the square root of 5? The square root of 5 is 2.236, which is the location of the x-intercepts that we found a moment ago. 2.236. Those were our x-intercepts. And so now that we know that I have an x-intercept at 2.236, which is really root 5, and I have another x-intercept at negative 2.236, which is negative root 5, we can actually finish our factorization where we say that our polynomial was, I'm going to write this whole thing out, x squared minus 5 times 3x squared plus 1. This finishes down as x minus root 5, x plus root 5, and 3x squared plus 1. And that brings us to the end of the factorization. We can't actually factor this last bit because it doesn't actually produce x-intercepts. So it's not factorable and it just stays like that. And that's the end of our factorization problem. So going back to the graph that we wanted to draw from the very beginning, we now know that our x-intercepts were at positive root 5 and negative root 5. And the graph comes down, goes through, and back up. I tell you what, as I said, this problem goes a little bit beyond what I'll test you on, but nevertheless, it's still an interesting example of what could potentially happen. And what could potentially happen, again, is that it could be that none of your x-intercepts are whole numbers or fractions. That they are, in fact, all square roots. But I'm telling you right now, I'm not going to do that to you. Okay? But this was still an interesting exploration of what could potentially happen with a polynomial problem. Yep, that's all I have to say about that one. Anyone want to ask any questions? I realize that got a little hairy at the end there because we did the additional factoring and then we had to find the x-intercepts by doing the zero product rule. Okay, well that's it. Let's try one where it actually is going to factor. I didn't intend for us to have something like that. Let's check number 10. Let's first, I'm going to go ahead and check number 10 and make sure that it does not have the square roots in it. 2x to the fifth, plus 3x to the fourth, minus 8x, minus 27. So this one, two of that, well, there's a, so it's the negative 1.732 and the positive 1.73. That's plus or minus root 3. And then the other one is negative 1.5, which is 3/2. This one, but it's actually good. Nope, everybody cross out number 10. Oh my goodness, that was a, yeah, cross out number 10 and we'll proceed. All right. Okay, this is going to be a good one. Number 11, we're definitely going to do number 11. That could be our last one. Both of those are good. Okay, number 11 and 12. Number 11 and 12 are going to be normal examples. I apologize for that last example. I hope that didn't shake your confidence too much. Let's do these two. Now notice that on these particular problems it says solve the polynomial inequality. And you'll notice that there's a greater than symbol instead of an equals to sign. And in this problem you have a less than or equal to instead of an equal sign. We'll come back to that at the very end. Let's just for now look at number 11 as though it's a normal polynomial. And we're going to do a similar analysis. Starting from the beginning, looking at all the parts and pieces, and then making a good graph. All right, number 11. So everybody, you can start by writing it down as a normal inequality. So f of x. Let's do this problem before we go on a break. I want to end on a high note here. So negative 2x cubed plus 19x squared minus 49x plus 20. And for the time being, let's just pretend that that says equal to 0. So we're just interested in that polynomial, and we want to factor the whole thing. This is going to be the whole process. And once again, what's our end goal? Graph. We want to make a graph. So I'm going to come over here and I'm going to start my graph. Okay. So our analysis begins by just looking at the end behavior and the y-intercept. So I know I have this end behavior. I know I have this y-intercept. My end behavior is a cubic, but it's negative. So what is that shape? It's cubic, but it's negative, so it's up to the left and down to the right. So this is my end behavior. I also know my y-intercept is 20, so I've got a 20 up here. Now this graph is pretty small. I'm going to end up doing a larger graph later on, but I just want to start a sketch of what my graph is going to look like. So far, that's what I know about my graph. I have a y-intercept of 20, and that's what my end behavior will look like. All right. This rational roots theorem is going to be a good one. So, by the rational roots theorem, or the rational zeros theorem, we take every factor of the last term and divide it by every factor of the first term. So, our last term is 20. Now, you might want to make a factor table just so you can see all the numbers. So, 20 is 1 and 20, 2 and 10, and 4 and 5. Anything else multiplied to make 20? I think that's it. So I'm going to write those out in order. So that's 1, 2, 4, 5, 10, and 20. And then the first term is a 2, so all the factors of 2 are just 1 and 2. This is a really good example for the rational roots theorem because you have to make every possible fraction. How many possible fractions are there? You'd have everything over 1, so 1 over 1, 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, 20 over 1. But then you'd also have every possible number on top over 2. So 1 over 2, 2 over 2, 4 over 2, 5 over 2, 10 over 2, 20. So what are all those numbers? Everything over 1 is just itself. So that's 1, 2, 4, 5, 10, and 20. But then we also need every top number over the number 2. So let's write those down in turn. I could have 1 over 2, which is 1/2. I could have 2 over 2, which is, what's 2 over 2? It's 1, and I already have that on my list. Then I could have 4 over 2. What's 4 over 2? Just 2, that's already on my list. I could have 5 over 2, that's a new number. I could have 10 over 2, but what's 10 over 2? Just 5, that's already on my list. And I could have 20 over 2, which is 10, but that's already on my list. So there, that's the rational roots theorem. It states that any of those could be my x-intercepts. That's a long list to check. Yeah, that is a very long list to check. So any of those numbers, plus or minus, those are where the potential x-intercepts are that are whole numbers or fractions. There could be square roots, but we're going to look at the graph. This one doesn't have square roots. Okay, next is Descartes' rule of signs. So Descartes' rule of signs, we're just going to write down the signs. So for the original function, my signs are negative, positive, negative, positive. And so the total number of sign changes is negative to positive is 1 change, positive to negative is another change, negative to positive is another change. So that's 3 sign changes. And remember, once you write down that initial number, you start subtracting by 2. So 3 minus 2 is 1. And then minus 2 again is negative 1. But you can't have a negative number of x-intercepts, so that's it. So what this tells me is that my function is either going to have 3 positive x-intercepts or just 1, well, or none. No. Sorry, 0 is not an option. You're either going to have 3 positive x-intercepts or 1 positive x-intercept. And that's guaranteed. It's either 3 or 1. Okay, now we're going to write down f of negative x. So we write down all the signs, but you change the odd numbered ones. So my odd term, that's a negative, so I'm going to make it a positive. My even term stays the same. My odd term changes, so negative to positive. And my last term stays the same. Well, how many sign changes do we have? None. So the number of negative x-intercepts is strictly none. That's really interesting. You see the way I already drew my tail? My tail's not going to be over there because there is no negative x-intercept at all. I'm only going to have positive x-intercepts. Yep, sure enough, look at the graph. Our graph, where are all the x-intercepts? Only over on the right-hand side. And how many are there? 3. So Descartes' rule of signs told us 3 or 1, so it turns out it's going to be 3. But for sure, there were none over on the left-hand side. So Descartes' prediction that there were no negative x-intercepts is correct. All right. So where does that leave us? On my drawing, I'm going to make a better sketch here. What I know now is that I'm going to have my positive y-intercept of 20. And then I'm either going to have 1 or 3 x-intercepts over here, but I'll still have a tail going up and a tail going down. And that's what I know so far. So at this point, you would do synthetic division. So let's write down our coefficients. Our coefficients for synthetic division are -2, 19, -49, and 20. And at this point, if you didn't have any technology at all, you would just start working your way through this list. Paris? No. Okay. However, I'm telling you that we can all be friends, and we can just use your graphing calculator to see which x-intercept on that list would actually work. And we know our answers are 0.5, 4, or 5. So knowing now that it's 0.5, 4, or 5, go to your list from the rational roots theorem and actually circle those. It was 0.5, 4, and 5. Those are the x-intercepts that it actually turned out to be. Which one do we want to do the synthetic division first? Yeah, why not do 4? So let's go ahead and do synthetic division with a 4. So we drop our first term, do multiply, add, multiply, add, multiply, add. All right, so that synthetic division did in fact work. This is where we are now. So 4 was an x-intercept, which means the factor is x minus 4. This started as a cubic, so now it's x squared, x no x. So now it's negative 2x squared plus 11 x minus 5. And then plus the 0, which I won't even write. So far, we've taken our original cubic polynomial and we've factored out one factor. Let's take a look at this next chunk. And this actually goes back to Josh's question. Josh said, now that we've reduced this polynomial, do I have to keep looking through that list, or could I do a new rational roots theorem just using 5 and 2? And you'll notice now that if I do rational roots theorem all over again, 5 over 2, that's much easier. All the factors of 5 are 1 and 5. All the factors of 2 are 1 and 2. My list now of fractions is either 1 over 1, 1 over 2, or 5 over 1, 5 over 2. That's a much shorter list of x-intercepts to look through. So is that a good response to your question, Josh? Yeah. However, we still already know what the x-intercepts were. And I want you to notice, right now, could you just factor this? It's a quadratic. Could you just factor it? You could just factor this. So I just want to show it to you. Don't anybody write this down. But since this is a quadratic, you could just factor it. So, you do the first times the last, that's 10. 1 multiplies to make 10, 1 and 10, 2 and 5. What adds to make 11, 1 and 10. So I could rewrite this as negative 2x squared plus 1x plus 10x minus 5. I could factor by grouping. Again, no one write it down. This isn't what we're actually going to do. I'm going to pull out the negative x, that'd be 2x plus 1. I'm going to pull out a 5, that'd be 2x plus 1. And then I would have 2x plus 1 times negative x plus 5. But I need to pull out that leading negative, so I'd write a negative 1 out front of 2x plus 1 and x minus 5. Okay, so we could do it this way. But check it out. Now that we know about synthetic division, we could go ahead and do synthetic division on this. So everyone write this down with me. Now let's do synthetic division on negative 2, 11, and negative 5. And we can use synthetic division to factor this. Now, we already know what number to use. We already did 4. So what do you want to do, 5 or a half? What, Jessica? 5. Yeah, 5 sounds better, right? Let's do 5. So if I use 5 now, then I'm going to do synthetic division one more time. I drop the negative 2, multiply, add, multiply, add. This is really cool. Now what does this give us? I started out as a quadratic, so now this is just x, no x. And I bring down the 5, and then this term. So now that's x minus 5, and that's negative 2x plus 1. And breaking down the x minus 4. And by the way, was x minus 5 and negative 2x plus 1? Well, what did I do there? That looks different. Right, but if I pull up the negative, I seem to have a different sign. This is, I have 2x plus 1. I did that wrong. I did that wrong. It's 2x minus 1. Well, I'm glad no one wrote that down. It's 2x minus 1. That'd be 2x minus 1. That'd be 2x minus 1. There we go. So now, yes, if I pull out the negative from the 2x minus 1, I'd have negative 1 times x minus 4 times x minus 5 times 2x minus 1. And you'll notice x minus 5 and 2x minus 1, x minus 5, 2x minus 1. Synthetic division gave me the same factorization as this log method. So you actually have two different choices. You could do synthetic division on a quadratic, and it will give you the factorization that you would otherwise have to do this long form of factorization with. And by the way, does everyone feel okay about how I pulled the negative out of the 2x plus 1 and I put it all the way in the front? You're allowed to do that, because I want to factor out the leading negative from the negative 2x plus 1. So I factor out a negative, which changes both of those signs, and then I put the negative 1 all the way up front. So where does that leave us? We are now done. Our polynomial, which started out as a cubic, is now, I'm going to come back here to write my final answer, is f of x equals negative 1 times x minus 4 times x minus 5 times 2x minus 1. So that's the factorization which tells us now our x-intercepts. Notice that this, to get these x-intercepts, there's a little bit of work that has to be done here. So what's that x-intercept? Just 4. This x-intercept? Just 5, because you can just change those signs. What about this one? I didn't know what that x-intercept is. You can't just change that -1 to a positive 1 and say it's a 1, because there's a 2 right there. So how do we turn this factor into an x-intercept? What?
You have to solve for x.
Yeah, exactly. You have to do the zero product rule. That's what you're supposed to do all the way along. Is you set that equal to 0, you set that equal to 0, and now you set this equal to 0. So 2x minus 1 equal to 0. You move the 1 over, 2x equals 1, and then divide off the 2, x equals 1/2. And so that's our other x-intercept. So our x-intercepts are x equals 4, x equals 5, and x equals 1/2. Which then, on our graph, we would have our x-intercepts at 1/2, 4, and 5. 1/2, 4, 5. And so, we draw my tail with slice, slice, slice. Yep. I think that's the end of the problem. Now, to be fair, this problem actually said solve the polynomial inequality. So I want you to notice this just takes one small extra piece of effort. When is this polynomial greater than 0? What does that mean again? Greater than 0? What are we looking for? When is the graph above the x-axis? So when is the graph above the x-axis? Between 4 and 5 and to the left of a half. So the technical answer to that question is, answer. To the left of a half, so that being negative infinity to a half, union between 4 and 5. I throw this out there just to show it to you. That you can also ask the question, when is a polynomial above the x-axis, or when is the polynomial below the x-axis? Because you would still just look and say, well, when is the graph above the x-axis? It's above the x-axis to the left of a half, which is negative infinity to a half, an interval notation, or between 4 and 5, which is the interval between 4 and 5. Whew. That's a lot of analysis, isn't it? It is a lot of analysis. Okay, well, we're going to stop there. You can cross out number 12. We're not going to do that problem because we still have more problems to practice. But that'll be in our next and last section where we talk about imaginary numbers. Quick question. Do all of you still have this packet that I gave you a long time ago? It says Introduction to Quadratics and Negative Numbers. I'm sorry, Introduction to Quadratics and Imaginary Numbers. I put it on the back table a long time ago. I'm hoping you still have it somewhere. If you don't, then I need to go get you a couple other examples. Sorry, a couple other handouts from my office. So let's take our break. The time is 9:16. Let's get back together at 9:26. And in case you don't have that, I'm going to run to my office and get a couple more copies. Yeah.
So for 2 assignment, it's still 3.1,
Yes, 3-1 is
and then 3.2 and 3.3.
next. Hi, folks. Let's get started. Shout outside. All right, folks. So, does anyone need this packet? Because I do have some extra copies. Okay. Where? Hey, Victor, here you go. Sure. Does anyone need this copy? That's okay. I think we have more people. Well, I'm going to get started. Everyone here has one? Okay. So, this is very interesting. We're going to talk about imaginary numbers and how this plays in to everything that we've been doing so far. So starting up at the top there, you can write in some notes. What is a linear equation, first of all? I mean, this is just kind of review. In fact, we can do this pretty quickly. What is the linear equation, or what is the linear equation? What's the equation of the line?
1 plus mx.
Very good, thank you, Jessica. Mx plus b, right? And why do we use the word linear? Why, Jackie? No, you know. We call it linear because it's a line, right? So it's the adjective form of line. So mx plus b is just a linear equation. It's an equation of a line. And what is the quadratic equation? Yeah, ax squared plus bx plus c. And now why do we call that quadratic? Not nearly as obvious. Linear comes from the word line. So quadratic comes from the word quadra. Quadra is the Latin prefix, which there's actually two different meanings. One means four, like a quadrilateral. Quadrilateral means four-sided. But technically, quadra actually means square. So when we think about a quadrilateral, on the one hand, it does mean four-sided, but quadra also means the word square. And so what about ax squared plus bx plus c is a square? Because whether you're looking at that equation or a graph of a parabola, none of those are literally a square. So what about this is a square? Yeah, the x squared term, right? So we use the word quadratic to refer to that term right there. Because you'll notice if I just cover up the ax squared term, what am I left with? Just a linear equation, right? So if I take away the quadratic part, it's just a linear equation, mx plus b. It says bx plus c, but mx plus b, that's a line. So the ax squared is the actual quadratic component. So when we refer to this whole thing as quadratic, these parts over here are quadratic. That's a linear equation. But this term right here is quadratic. And the reason it's quadratic is because of the square right there. The exponent that's a 2. In our English language, we refer to that as squared. And so we call it quadratic. Okay, so what does it mean to find the solution of a quadratic equation? We've already talked about that. When you have any quadratic equation, you're going to find the solution. So like, let's say that I had, x squared plus 4 equals 0. So I just have some quadratic equation. I want to solve it. To solve it means to find the x-intercepts. And you either have 0 x-intercepts, 1 x-intercept, or 2 x-intercepts, which means that this equation either has no solutions, 1 solution, or 2 solutions. And that's what you can expect up front. This particular equation, if you'll notice, as soon as I move that 4 over, I have x squared equals negative 4. Both sides. I have x equals plus or minus the square root of negative 4. What is the square root of negative 4? Nothing. It's imaginary, right? Your calculator would say error. And so how many x-intercepts does this graph have? None. There are no x-intercepts to that graph. And in fact, if I graph this equation right here, it would be that parabola just like that. So indeed, x squared plus 4 as a graph has no x-intercepts. And indeed, the algebra bears that out because if you actually solve for x, you get an imaginary number, which your calculator would say error, no solution. So this particular quadratic has no solution. It has no x-intercepts. And yet, what we would like to do in mathematics is still say that this thing has solutions. What we'd like to do, ideally, in mathematics is say, whatever the highest power of x is, that's how many solutions there are. So even though there are no x-intercepts, we all would like to still kind of like tongue-in-cheek, there are 2 answers. Like we'd like to be able to say that this thing has 2 answers. And so what mathematicians did is they said, well, you see that square root of negative 4 there that your calculator says no answer? What we'd like to do is just go ahead and say the positive square root of negative 4 is an answer, and the negative square root of negative 4 is an answer. And we'd like to go ahead and call those things answers anyway. Even though your calculator says error, we just like to be able to go ahead and write them down, because that way we can say, generally speaking, that whatever the highest power of x is, that's how many answers there are. And even though these answers, your calculator won't tell you that they're answers, we'd like to go ahead and call them answers anyway. And that was the origin of imaginary numbers many hundreds of years ago, was this desire mathematicians had to write down answers anyway, even though there weren't any. Okay, well, let's keep going. The last question, what's the quadratic formula? We've already talked about that. The quadratic formula gives you the, what does the quadratic formula give you? The negative b plus or minus square root of b squared minus 4ac over squared? It tells you the x-intercepts, right? So x-intercepts are very important. No matter what, x-intercepts for sure are the answers to an equation. But we'd like to be able to say, even if there aren't any x-intercepts, we'd like to say that there's an answer to this equation. So let's turn it over and keep talking. Now, first of all, is this what you have on the back? Yeah? Yeah, it is. This is just a quick reminder. We did this maybe a couple weeks ago, but let's just all do a quick reminder how to simplify a root. So let's see. I remember doing some of these with you. Let's try one of these. What's this? How do you simplify the square root of 125? We're in the square root of 125. How do we simplify that? So first of all, you go to where 125 would be on your list of square numbers. So there's my list of square numbers up at the top. That's where 125 would be. And then what do? Selenite, go ahead. You start moving it to the left, and you find the first number that divides into 125. So what's the first number that divides into 125? 25. We did this together, right? Yeah. So 25 goes into it. So you'd rewrite 125 as 25 times what? 5. And then you split that root apart into root 25, root 5. And then because you specifically chose a square number, now that part you can actually square root. The square root of 25 is just 5. So root 125 is the same as 5 root 5. If you type both of those into your calculator, you will get the same decimal. I would encourage you to try it. If you type in root 125, you get the answer 11.1803. And if you type in 5 root 5, you get the answer 11.1803. So either way, you're going to get the same decimal answer, but it's going to be very valuable to us to be able to simplify roots. So one more time, just to be sure that we're all on the same page here. How could I simplify root 162? Let's simplify root 162. We'd go to where 162 is on my list, which is about there. And then you start moving to the left. And what's the first number that goes into root 162? Yeah, 81 goes into 162. So I would rewrite root 162 as root 81 times 2, which becomes root 81 root 2, which is 9 root 2. So root 162 simplified becomes 9 root 2. And that's the procedure. You take any given number, you rewrite it as the product of a square number times a non-square number, and then you split the root so that you can simplify the first part of the root, and the second part of the root just stays a root. So that's how you simplify a root. Questions on simplifying a root? Now, again, you might have learned a different way of doing this. You might have learned the factor tree method, but I'm going to be doing this method today when we talk about imaginary numbers. What's that, Josh? Yeah, and that's fine. You know, you could still do that. If you had the 162, and then you could break that down into 2 and 81, and then break that down into 9 and 9. And at that point, you could be done. You could say root 162 is the same as root 2 times 9 times 9. And what would you do next, Josh?
Pull the 9s out.
Yeah, you just pull the 9s out, and that gives you 9 root 2. And you can see it's the same solution we got, but it's using the factor tree instead. Okay, that's it for that page. Okay, historical interlude. Just real quick. Long, long ago, humans didn't even have a concept for negative numbers. So I'd like you to consider the problem 5 minus 9. If you go back long enough, and you ask somebody what's 5 minus 9, they would have laughed at you and said, you can't do that. Like if you have 5 sheep, and you try to take away 9 sheep, that's just impossible. Right? So if you go back thousands of years and you just found a human and you were like, hey, what's 5 minus 9? They would have just laughed at you and said, that's impossible. Okay? To them, 5 minus 9 didn't make sense, and to them, that would have been imaginary. They would have said 5 minus 9. That's imaginary. There's no such answer. Okay, and then long ago, humans didn't even have a concept for a number that wasn't a fraction. So the number root 2, there was a time where that was considered not just imaginary or not real, but even sacrilegious. Like root 2, every number has to be expressible as a fraction. So if you go back just 2,000 years ago, humans thought every number could be expressed as a fraction. But then they realized that the square root of 2 could not be expressed as a fraction. This is an irrational number. And in the very beginning, humans really didn't like that idea, that you could have a number that wasn't a fraction. So again, that they would have considered imaginary, that you couldn't express a number as a fraction. And then, until recently, I would say around the 1500s, it was considered impossible to square root a negative number like the square root of -1. And even to this day, most of your calculators, if you type in the square root of -1, it'll say error. And that's how they felt about it in the 1500s, that you couldn't square root a negative. Mathematicians said it didn't make sense, like dividing by 0. To this day, we all agree you cannot divide by 0. That's imaginary too. Like you can't divide by 0, there's no answer. Well, history shows again and again that what was once considered impossible is no longer impossible. So in the history of mathematics, we take something, they're like, well, you can't do that, and then we say, okay, you can do that. And we change our mind about it. And I just love Star Trek, The Next Generation, Jean-Luc Picard. I don't know if any of you watch that particular Star Trek, but he has a great quote and he says, something is only impossible until it isn't. And I think that's a really cute and clever quote. So let's look at the history of mathematics that led up to being able to square root a negative number. So looking all the way up at the top there, it says we want all equations to have solutions. So first of all, what is a solution? We need to be able to write that down in 2 different ways. So I gave you 2 lines. I'd like you to write down 2 definitions of what a solution is. So what's definition 1 of a solution? What does it mean to find a solution to an equation? The what? The roots, which are the x-intercepts. So one definition of a solution is graphically the x-intercepts. Okay? So when we say that an equation has a solution, what we're referring to is the x-intercept. You take that equation, you graph it on Desmos or on your TI, and you look at the x-intercepts. And whatever the x-intercepts are, those are the solutions. The second definition, though, of a solution, right, is a solution is a number you plug in to make the equation true. So that's actually 2 different ways to define a solution. Both of those definitions are correct, but they're not actually the same. Because there are solutions, as in numbers that you can plug into an equation to make it true, that won't show up as an x-intercept. So all x-intercepts are solutions. That is a number that you can plug in to make the equation true. But not every number that you can plug in to make an equation true is going to be an x-intercept. So let's consider this next example. What is the solution to x squared minus 1? So if we have x squared minus 1, what's that solution? Let's consider both. If I just graph that first of all, so definition number 1, if I graph that, I get this, and my x-intercept is at 1 and negative 1. That's what the graph would show you. So if I graph x squared minus 1, I put it on a graphing calculator, I look at the graph, I'll get the 2 solutions, 1 and negative 1. That is, I'll get the 2 x-intercepts, 1 and negative 1. Okay, so that's the first definition. What about the second definition? Now you just do algebra. So I move the 1 over, I get x squared equals 1, I square root both sides, and I get x equals plus or minus 1, which means x equals positive 1 and negative 1. Now, even now, this process is not done. When we say we do algebra, it means you do the process of algebra, but then you actually take those numbers and go back and actually plug them in and check to make sure that it makes the equation true. So now, if I take my equation x squared minus 1 equals 0, and I plug in the number 1, is that true? Is 1 squared minus 1 equal to 0? 1 squared is 1 minus 1 is 0 equals 0. Is that true? Yeah, that's true. And then what about something squared minus 1? What if I plug in negative 1? Will that still be true? So negative 1 squared is still 1, 1 minus 1 is 0. So that's also true. So I'd like you to notice that the first definition of solution didn't take that long to do. Right? You just graph it on your graphing calculator, you look at the x-intercepts, and you're done. The second definition of a solution took me a little bit of time, because I actually had to take my equation, do algebra, and then take my answer, plug it back in, and verify that it made the equation true. So you'll notice that second definition, a number you plug in to make the equation true, that process is much longer. And it takes a little more effort, because you actually have to do the algebra, then after the algebra, you actually have to plug it back in, and then verify that it made the equation true. Okay, so that was that problem right there. So what is the solution to x squared minus 1? Prove your solution is true. Well, we just did in 2 different ways. Okay, so now let's look at the next equation. The next equation, it says, what's the solution of the following? X squared plus 1. So now I have x squared plus 1. Now if we use the first definition and you graph that, you'll have a graph that looks like this. So are there any x-intercepts? No, there are no x-intercepts. And so at face value, you might look at that and say, this equation has no solutions. And that would be the state of affairs in the 1500s. So, 1400s, 1500s, mathematicians would have looked at this equation and said, there's no solution. In fact, they would have looked at that, much like early people looking at 5 minus 9. They would have said, there's no solution to that. You have 5 sheep, you can't take away 9 sheep. That's just silly. And they would have looked at x squared plus 1, and they would have said, there's no answer to that. There is no number that you can square, and then add 1 to it, and get 0. However, mathematicians were all on the same page in that if you have x to some power, they want that number to represent the number of solutions. So it's very dissatisfying to them to see x to the power of 2, and they would say to themselves, well, gee, there should be 2 solutions. But then they look at the graph and they're like, darn, there aren't any solutions. So they wanted to come up with a new way of defining what a solution even was. And so now everybody do the algebra with me. They said, well, let's just do the algebra anyway. Let's move the 1 over and get x squared equals negative 1. And then square root both sides, and that gives us x equals plus or minus the square root of negative 1, which is positive the square root of negative 1 and negative the square root of negative 1. And this left them with an uncomfortable choice. On the one hand, we all know that there's no x-intercept, so there should be no solutions. On the other hand, that's an x to the power of 2, so I really want there to be 2 solutions. And here are my 2 solutions, except for the fact that the square root of negative 1 isn't a thing. And if you type it into your calculator, it says error. And so the mathematicians pushed through, and they did the uncomfortable thing, and they said, let's call that a solution anyway, so that we can say that x raised to any power, that number represents the number of solutions. Let's just call these things solutions anyway. And so what do we need then? If we're going to call these solutions, we needed to satisfy definition number 2. Not definition 1. Definition number 1, there is no x-intercept. So we're just stuck there. There's no x-intercept. However, definition number 2, let's plug this in to the equation and see if it makes it true. So everyone try this with me. Take your equation x squared plus 1, which is something squared plus 1 equals 0, and plug in the square root of negative 1. Does that make the equation true? Because now what happens when you square a square root? Anytime you square a square root, what happens? They cancel out. So the square root and the square cancel out, and they're left with negative 1 plus 1. And what is negative 1 plus 1? It's true. So that's great. Apparently this thing is a solution, because it is a number that I can plug into the equation and it makes it true. Same thing would be true for this negative root negative 1. If I go ahead now and I write down my equation again, something squared plus 1 equals 0, and I plug in negative root negative 1. Well, first of all, what happens when you square a negative? What's a negative times a negative? Positive. And then what happens to this when you square a square root? They cancel out. And so that still becomes negative 1. And once again, negative 1 plus 1 is 0. And once again, it's true. So that's the decision mathematicians ended up making, is they said, listen, the number of x-intercepts could be less than the number of the exponent. Well, let's go ahead and call these things solutions anyway, so that we can stick to our guns and say that the highest exponent on the highest exponent on x tells you the number of solutions. That is the number of numbers that you can plug into an equation to make it true. So ever since that decision was made, and again, say the 1600s, the highest power on x is always the number of solutions. That is the number of numbers that you can plug into the equation to make it true. It's not necessarily the number of x-intercepts, but it for sure is the number, the quantity of numbers that you can plug in to make the equation true. Okay, so all that said, moving on, does the value root -1 have any true meaning? Like, does this thing really have a meaning? No. Right, it really doesn't. Because if you type it into your calculator, what do you get? Error. All right, furthermore, there is no, what I really mean by this is, there is no number on the number line. Okay, so consider all the numbers on the number line. There is no number on the number line that this thing is actually equal to. So no, the square root of -1 is not a real number. It's not a real number. You won't find it on the number line. But we go ahead and say that it's a mathematical object anyway. So does root -1 have any true meaning? No, but we go ahead and we call it a mathematical object. Now, so conceptually recall the meaning of root 4. Let's do this. So the square root of 4 means what? It means find a number that's squared equals 4. So what number squared equals 4? What number can I put right there? 2. Or what other number can I put there to make it squared equal 4? -2. So that's why the square root of 4 really is equal to plus or minus 2. Because if you square the 2, you'll get 4. If you square the -2, you'll get 4. So now consider the square root of -1. What number squared will equal -1? Well, first of all, what if I put a positive number in here? What's a positive times a positive? Positive. So it can't be a positive number. What if I put in a negative number? What's a negative times a negative? Still positive. What if I put in 0? Then what's 0 times 0? Still not -1. So is there any number that I could possibly square to make it equal -1? No. And that's why we say it's nonsense. Right? There is no real meaning. Whatever this is equal to, it's not on the number line. It's not a positive number. It's not a negative number. It's not 0. But we're just going to go ahead and call this something anyway. And so, all the way down to the bottom now, mathematicians give the square root of -1 meaning by calling it imaginary. We call it the imaginary number. And thus, we all agree to define, so jot this down with me here. The definition is that we're going to call the square root of -1 equal to the letter I. And that's it. So for hundreds of years now, the mathematical community has simply agreed that the square root of -1, though it not be equal to anything, we will call it by the letter I. Which also means that, we're just defining the square root of -1 to be the number I. Which also means, what happens if I square both sides? If I have I equal to the square root of -1 and I square both sides, what is I squared equal to? Just -1. So these are our two key definitions that we're going to take with us for the rest of this analysis. So I'm going to write it up here nice and big so we all see it. I is the square root of -1, and I squared is equal to -1. And if someone were to come up to you and ask, hey, what's the deal with this I is equal to the square root of -1 business? Like, my calculator doesn't do the square root of -1. It says error. Why do mathematicians mess around with it? What would you say? Why do we mess around with I? Why do we say it's equal to something even though it's not equal to something? What would be the answer? Well, I appreciate that you threw out an answer there, Josh. I don't know if you can graph it, because you can't graph the square root of -1. Like, it won't show up on the graph. It won't be an x-intercept. But it has to do with this right here. Why do we go ahead and call the square root of -1 something? Because we want, what do we want that 2 to represent? The number of solutions. We want the highest power on x to represent how many solutions the equation actually has. And so that's why mathematicians had this definition of I is equal to square root of -1, because we want to be able to say, hey, if you have a polynomial, and it says f of x equals x to the third, I want to be able to find 3 objects that I can plug into that function and make it true. And so I, the letter I now, is one allowable object that we can plug into an equation to make it true. So, anybody have any questions about all that? That was just kind of like a little brief historical interlude in which we talked about the origin of imaginary numbers. No? All right. Well, let's go ahead and try it a couple times. Taking a look at the next page, we need to be able to compute with imaginary numbers. So it says, how do you simplify perfect square roots, but that are negative? So we're going to do all, well, at least the first couple of these. First of all, on your calculator, what's the square root of -4? 2. Well, you are correct. Some of your calculators will actually say 2i. But most of your calculators will say error. Okay? But there is actually an answer. And so here's how you do it, folks. You know how, well, we're going to rewrite this square root of -4. We're going to rewrite it as root 4 times root -1. Hold on, let me show all my work. What we're going to do is rewrite that as 4 times -1. What you always do when you have a square root of a negative number is you chunk off the negative part, the -1, and you put it at the end. So now what we can do is we can break apart this root and call it root 4 times root -1. And the square root of 4 is simply 2, and the square root of -1 is simply I. So the square root of -4 is 2i. And that's what some of your calculators will tell you. But most of your calculators will just say error. But now we all know that the square root of -4 is actually 2i. Let's try that again. What if you have the square root of -25? Again, you would chunk off the -1, and you would call that root 25 times -1, which then you can completely chunk off the -1, so that's root 25 times the square root of -1. And then the square root of 25 is just 5, and the square root of -1 is I. Now, you can do that process over and over and over again. And then you'll eventually notice that pattern. And what is the pattern? That basically you can just take that negative sign and turn it into the I. Right? Anytime you have a root that's negative, you know that there's going to end up being an I. And you just do the square root like normal. So taking a look at the next one, the square root of -100, you could do that all in your head in one step. And you could say, well, it's a negative square root, so I know there's going to be an I involved. And what's the square root of 100? It's not like I'm trying to encourage you not to show your work. I just want you to know that that is possible to just do that square root in one step. So like, what's the square root of -121? On the one hand, the square root of a negative will be an I, and the square root of 121 is 11. Now, it's typically best to show your work, okay, even though I just showed you that it is possible to not. Let's take a look at root -12. So again, root -12, if you wanted to, you could immediately just call that root 12 with an I at the end. Right? So that would be allowable. So long as you want to be really careful that that I is now outside the square root and not inside the square root. And sometimes people will put a little drop down on the square root symbol to show that it ends at the end of the 12 and before the I. So that's one notation I've seen. But really, what I'd like to see you do, and do this whole process with me a couple times, you would take the square root of -12 and you would chunk it into 3 bits. Right? You've got the -1 that you chunk off at the end. And then how do we simplify 12? What's a square number that goes into 12? 4. So this would really be 4 times 3 times -1. you would say, okay, I want to find the square root of negative 12. I'm going to chunk that into my negative 1, which will be at the end. And then I need to rewrite 12 as a square times a non-square number. And so now I break that into 3 roots. So that's root 4 times root 3 times root negative 1. And that way, the first one will simplify. The square root of 4 is 2. The second one doesn't simplify. That just stays 2 root 3. Then at the very end, they're an I. And that's how you simplify a root that has a negative in it. You'll notice that we could have done that the first way by just immediately pulling out that negative as an I. I could have then just simplified the root 12. I could have called the root 12 now. That's 4 times 3, I. And then that'd be root 4, root 3, I. And then the square root of 4 is 2 root 3, I. So there are indeed a lot of different ways that you can show your work. So let's just try one more. How about the square root of negative 200? How would we break that apart? What square number goes into 200? What square number goes in? What's a square number that goes into 200? 100. 100 is a good square number. So that gives us 100 times 2 times negative 1. So that's a full separation of the number negative 200. Now I have the square root of 100 times the square root of 2 times the square root of negative 1. And so the square root of 100 is just 10. And then the square root of 2 stays root 2. And the square root of negative 1 is I. So the answer would be 10 root 2I. Now just so you know, some math books, they want to avoid the confusion that that I is under the square root or out of the square root. So what they'll often do is put the I in between the 10 and the root 2. That way there's no confusion at all that the I is not in the square root with the 2. All right? So that's how we simplify a square root with a negative in it. One more thing to look at is how do we actually do mathematics with an I? Like here, I have 2 different expressions that both have I's in them. How do we add them together? How do we subtract them together? And then also, how do we FOIL with I? And the good news is that doing math with I is exactly like doing math with a variable x. It's the exact same. Like, look at that first problem. If you wrote down, just to show it side by side, if I gave you the problem 5 plus 8x plus 10 minus 2x, what would you do? You would just combine like terms. So I've got 5 plus 10 is 15, and then 8x minus 2x is 6x. So that would be your solution. It works the same way if it's an I. So if you have 5 plus 8i, and then plus 10 minus 2i, you would still just combine like terms. 5 plus 10 is 15, and then 8i minus 2i is plus 6i. So for the most part, doing computations with I is exactly the same as doing computations with x. You just combine like terms like it's a variable. The only difference is that when we do computations with x, you don't know what x represents. In the case of I, we do know exactly what I represents. I represents the square root of negative 1. But you still do all of your computations the same. The only thing that's a little different is when you do FOIL. So everyone do the first FOIL problem with me. We have 3 plus 2i times 5 plus 4i. Go ahead and do FOIL just like you would do FOIL with x. First, outer, inner, last. So as a first step, did everyone get 15 plus 12i plus 10i plus 8i squared? Okay, so then what do we do? There's 2 more things to do. What's the first thing? We just combine like terms in the middle, so we have 15 plus 22i plus 8i squared. And there's one more thing to do here, which is different from normal FOIL with an x. If these were x's, we'd be done. But since it's an I, what is I squared equal to? It's just equal to negative 1. When you do computations with I, you replace any I squared with a negative 1. So now we have 15 plus 22i plus 8 times negative 1. So anytime you see an I squared, you get to replace it with a negative 1. So now that gives us 15 plus 22i minus 8. And so 15 minus 8 is 7. And so our final result is 7 plus 22i. So at the very bottom of your page, I think what I meant for you to write down here, multiplying complex numbers is like FOIL. Just remember that I squared is equal to negative 1. So anytime you see an I squared, you get to replace it out with negative 1. All right, so that little packet that we just did, that was just a little interlude for me to give you some background on I and why we compute with I and the difference between an x-intercept versus a solution. So now let's proceed to section 3.4 in your main packet. And just so everyone knows, what we're about to do here is we're just going to practice computing with I a little bit. That sounds like bad grammar, doesn't it? We're going to practice with I. We're going to practice a little bit, and then we're going to go back to the original question of how do you factor a polynomial? So we're just doing a little bit of practice with I, and then we're going to go back to factoring polynomials. I tell you what, we don't have to do all of these. We're just going to set them up. So look at number 1, for instance. It says, let z equal negative 5 plus I, and let w equals 4 plus 2i. These are just two numbers. Right? We call this a complex number because it has a real number and an imaginary number. So that's what our z is, and that's what our w is. And they'd like us to do a couple of computations. So let's introduce these computations and do them real quick. So part A, they want z plus w. So we write down what z and w are. Z is negative 5 plus I, and w is 4 plus 2i. And what do? We just add them together, combine like terms. So we have negative 5 plus 4 is negative 1, and then I plus 2i is 3i. How about part B? It says find z squared. So z, again, is negative 5 plus I. So how do we square that? How do we square negative 5 plus I? How do you square any binomial? What do you technically have to do? Okay, you multiply it times itself. So we're going to do negative 5 plus I times negative 5 plus I. And then you FOIL. So make sure whenever you see a binomial squared, you actually have to write it out times itself and then FOIL. Every once in a while we get a little excited and we just square both terms, but that's incorrect. You have to technically do FOIL. So first, negative 5 times negative 5 is 25. Outer, negative 5 times I is negative 5i. Inner, I times negative 5 is negative 5i. And then last, a positive I times a positive I is a positive I squared. Then what? Combine like terms. So that's 25 minus 10i. And what do we get to do with the I squared? Yeah, we get to replace it with a negative 1 because I squared is equal to negative 1. So that's really minus 1. So now we have 25 minus 10i. The I squared is really a negative 1. And so now 25 minus 1 is 24 minus 10. I crossed out part C, but I would like to do D and E. So there's a new notation that they introduced to us, and the notation is putting a bar. This bar is brand new notation and only works with imaginary numbers. And the bar means a conjugate. So I think we already talked about conjugates. How you'd have two numbers, one with a plus and one with a minus. I know we've already talked about conjugates because we did say something like x squared minus 25, and the fact that you can factor that into x plus 5, x minus 5. So these are called conjugates. They're the exact same numbers, x and 5, except one is plus and one is minus. And so when we talk about imaginary numbers, let's say that you have the imaginary number 3 plus 2i and the number 3 minus 2i. We call these conjugates as well. And so if somebody hands you an imaginary number, like 5 plus 7i, and they said, what's the conjugate? You would just write down 5 minus 7i. So the conjugate of 5 plus 7i is 5 minus 7i. You keep the same numbers, but you change the sign from plus to minus. If somebody gave you 3 minus 6i, and they said, what's the conjugate? You would write down 3 plus 6i. It's the same numbers, but you change the sign from plus to minus. So conjugates are simply a pair of numbers where one of them is a plus and one of them is a minus. So, and that's what the bar on top means. So when we look at z bar, it means take z, which is really negative 5 plus I, and so z bar would be negative 5 minus I. Which sign got changed? Not the sign on the 5, but rather the sign on the I. That makes a little bit of sense. We're not changing the sign on the real number, we're changing the sign on I, because after all, when you do a square root, like let's say that I had x squared equals negative 1, and you square root both sides, what is the actual answer? Plus or minus root negative 1, which is really plus or minus I. So the I is already kind of inherently a plus or minus object because we arrived at I by square rooting a negative 1, and when you square root, it's typically plus or minus. So it's the imaginary part that gets changed from plus to minus when you conjugate something. So just as one more example, what if I wanted W bar? And by the way, you just say bar, W bar. So first of all, W is what, 4 plus 2i? So what's the conjugate W bar? 4 minus 2i. So the 4 stays positive, that's the real number part. It's the I component that changes from plus to minus when you do conjugation. Okay, one last neat example, z times z bar. There's something wonderful that happens whenever you multiply an imaginary number times its own conjugate. So let's find out what happens when you multiply an imaginary number times its own conjugate. So z was negative 5 plus I, and the conjugate of z was negative 5 minus I. And what we're exploring right now is what happens anytime you multiply an imaginary number times its own conjugate. So let's try it. We FOIL. So first, negative 5 times negative 5 is positive 25. Outer, negative 5 times negative I is positive 5i. Inner, I times negative 5 is minus 5i. And then last, positive I times negative I is negative I squared. So there's two observations we can make about multiplying conjugates. What's the first thing we notice whenever you multiply a conjugate? The middle terms will always cancel out. So when you multiply conjugates, the middle terms always cancel out. The second thing is the last term is always going to be an I squared, which means you get to replace it by negative 1. So that was a negative I squared, so that's negative 1. So double negative, that's really a plus. So now we have 25 plus 1, which is 26. So when you multiply two imaginary conjugates, the result is always just a normal real number. And why? Because the middle terms canceled out, and the middle terms are the only terms that are actually imaginary. The last term is not imaginary because I squared gets replaced by negative 1, that becomes a real number. And so anytime you multiply conjugates, you get a regular real number. Yep. So these are how we do basic computations with imaginary numbers. Let's see. We'll just do a couple of these together because we already kind of reviewed it. How would you simplify root negative 49? What would the answer be? The square root of 49 is 7, and then the square root of a negative becomes the I. So the answer is just 7i. Just be 7i for that first one. I will actually write it down. I just wanted to suggest it. So we'll do those first two together. Actually, we'll do all three. When you see root negative 49, you'd split that apart into root 49 times negative 1, which becomes root 49 times root negative 1, which is 7i. You'll notice that you have to be very careful and do step by step. This next one is root negative 25 times root negative 4. And I'd like you to appreciate, if you typed root negative 25 in your calculator, what would it tell you? Error. And if you type root negative 4 in your calculator, it'll give you error. So right now, what are we telling our calculator? Error times error. And it's pretty hilarious. Like, what's an error times an error? Like, your calculator sure doesn't know. And yet, if we now break these apart, I know that this would be 25 times negative 1, and this would be 4 times negative 1. And so I can break that apart into root 25 times root negative 1 times root 4 times root negative 1. And now I know that root 25 is just 5, root negative 1 is I, root 4 is just 2, and root negative 1 is just I. And now we can actually multiply these things. I can do 5 times 2 is 10. And I can do I times I, which is I squared. And what is I squared? Negative 1. So now that's really 10 times negative 1, which is negative 10. So in this particular case, error times error is actually equal to negative 10. Which again, your calculator would not have necessarily been able to tell you. If you have like a TI-82 or a TI-83, your calculator would have just said error. So this is truly a skill that you'd have to do by hand, unless your calculator's fancy. Now how about this last one? Root negative 25 times negative 4. Notice that this is subtly different. Inside the square root, I have negative 25 times negative 4. What's negative 25 times negative 4? That's actually just 100. Right, because the negative times the negative is positive. And so that's just 10. So that was a little different. This was inherently an imaginary number, because it was just the square root of negative 25. So that was definitely imaginary. Whereas here, both of those are underneath the square root. We're allowed to go ahead and compute whatever's in the square root. So negative times negative is positive, and then that's just 10. Okay. I tell you what. Well, we just have a couple minutes left, huh? We'll just do this last part, and then we'll roll over the last section to our next class period. The last part says, what are higher powers of I? This is an interesting question. What is a higher power of I? So notice here we have I to the 15th, I to the 26th, I to the 117th, I to the 304th. I look at this and say, well, now we're just being silly. Like we have this object called I, and it's already imaginary, and why are we going to raise it to all these powers? So let's just take a look and see what happens. What if I did? So we already have the answer that I is the square root of negative 1, I squared is negative 1. What would I cubed be? It is negative I. How did you know that? Oh, you're looking up there. Okay, well, yeah, exactly. But now let's think why. I cubed, I could actually write that out as, do you all agree, I squared times I. Can I do it like that? I can just chunk out an I squared, because now what's I squared? -1 times I, and what's -1 times I? Negative I. So that's where they got I cubed is equal to -I. Because we just chunked out an I squared, and we got the result -I. So now I'm going to add that to my list. I know that I cubed is equal to -I. So then what's I to the 4th? We'll do the same trick. What would I to the 4th be? Yeah, very good. I squared times I squared. And I squared is just -1. And I squared is -1. And -1 times -1 is 1. So now we know that I to the 4th is equal to 1. Well, that's really interesting. That if you take the imaginary number, the square root of -1, and raise it to the 4th power, it's actually equal to just 1. So then what's I to the 5th equal to? And likewise, I to the 6th, and I to the 7th, and I to the 8th, and so on. Well, let's start right there. What's I to the 5th? Move that up. I'm going to go right here. How could we solve I to the 5th? What could I chunk out? You could chunk out I squared and I squared, and so that could be I squared times I, right? Well, what can we do instead? We already know what I to the 4th is. Could I rewrite I to the 5th as just I to the 4th times I? That'd be even faster. What is I to the 4th? Just equal to 1, so that's just 1 times I, which is I. And so I to the 5th is equal to I again. And something really interesting happens with powers of I, and that is that they start to repeat themselves. So I is equal to I squared is -1, I cubed is -I, and I to the 4th is 1. And then it repeats the loop. I to the 5th would become I again. I to the 6th would become -1 again. I to the 7th would become -I again. And I to the 8th would become 1 again. And the answers will just keep repeating themselves over and over in a list of 4. And I could do that again. So continuing on from I to the 8th, I could do I to the 9th, I to the 10th, I to the 11th, and I to the 12th. The answers would repeat the same list, and it would then be I to the 9th is really I to the 10th is -1, I to the 11th is -I, and I to the 12th is 1 again. And we'll just keep going like that. So the takeaway here is you'd say, well, then what's a really big power? Like say I to the 15th. Well, we're almost there, aren't we? We could just keep writing it down. But writing it down takes a very long time. So there's a special trick, and it says right here, if n is a natural number that has a remainder of r when divided by 4, essentially what you do is you take the exponent and divide it by 4 and look at the remainder. So we're asking, what is I to the 15th equal to? You take 15 and you do long division. Hey, what do you know? Whoever thought we'd have to do long division since the other day when I mentioned it. And 4 goes into 15 3 times. 3 times 4 is 12. And then subtract and get a 3. I to the 15th reduces to I cubed. So you can immediately take your exponent, divide it by 4, and whatever your remainder is, I to the 15th is the same as I cubed. And then you only really have to memorize that short list. I cubed is really -I. We'll try 2 more of those, and then we'll say class is over. So what about that next one? I to the 26th? So what would I to the 26th be equal to? So I would take 26, I would divide it by 4. 4 goes into 26 6 times. So 6 times 4 is 24, and then you subtract that to 2. So I to the 26th is really the same as I squared. And what is I squared? -1. So now we know that I to the 26th is really equal to -1. Let's try one more. I to the 117th. So what is I to the 117th? You would take 117 divided by 4. So let's see, 4 goes into 11 2 times. That's 8, that's 37. 4 goes into 37 9 times. 9 times 4 is 36. And we have a remainder of 1. So I to the 117th is really equal to I to the 1st, which is just I. Now, at that point, you might say, Why on earth would we ever have to raise I to powers like that? And you're right. It's, probably a very rare thing that you would do. But it was interesting, nevertheless, to explore the properties of I. So those are some properties of I. And when we come back next time, we are going to factor a few more polynomials, which could have x-intercepts that are whole numbers, fractions, square roots, or imaginary numbers. And then we'll be done with chapter 3, and we'll move on to chapter 4. All right, thank you very much, folks.